Good morning, Professor Madhu.
Good morning. Yeah.
Welcome to the session, sir.
Thanks.
So, do you want to? I'm good, sir. How are you?
Thanks. Yeah, very fine actually. Yeah, I can share my screen. Yes.
Okay. Okay. Just let me make you co-host, and I will stop sharing from my side. Yes, sir. You can check now.
Okay. Just 1 second. So that should be okay, right?
Yes. Yes. It's coming.
Right.
Yeah.
Right. Thanks.
So, sir, we have 7 more minutes. We will start the session exactly at 11 o'clock.
Right. That's fine.
Okay. Thank you.
Hello, good morning, everyone.
So good morning, all. Welcome back to the fourth day of our faculty development program. Today, we have two eminent scientists from reputed institutions, Professor P.K. Madhu, TFR Center for Interdisciplinary Sciences, Tata Institute of Fundamental Research, Hyderabad, is going to talk on structure and dynamics through the NMR looking glass. And we'll have Dr. Pralay Santra, scientist, Center for Nano and Soft Matter Sciences, Bengaluru, who is going to discuss on X-ray photoelectron spectroscopy, a versatile tool to investigate materials. So we'll start with the first session on the day by Professor Madhu, a solid-state NMR expert. As you may know, solid-state NMR is one of the difficult areas to work on, and it is rare to find an expert in this field. Professor Madhu has developed various NMR instrumentation facility in TFR in both Mumbai and Hyderabad. So we are so lucky to have such an expert here with us today. Sir, we are so happy and grateful for you for accepting our invitation. To introduce Professor Madhu formally, I invite Dr. Shashidhar Bharadwaj, Department of Chemistry, Biochemistry, M.S. Ramaiah College of Arts, Science and Commerce.
Let me give a brief introduction of Professor P.K. Madhu, speaker of the session. Professor Madhu, presently working as a senior professor in Tata Institute of Fundamental Research, TIFR. He did his MSc in physics from IISc Bangalore and also doctoral degree from IISc Bangalore. Postdoctoral research from Weizmann Institute of Science, Israel, and also one more from Johannes Kepler University, Austria. He was visiting fellow in University of Stockholm, Sweden, and University of Southampton, UK. He joined TFR Mumbai in 2003. Later, he moved to TIFR Hyderabad in 2021. He is member of several editorial board. He has received National Magnetic Resonance Society NMRS Lecture Award and also a resource person for many workshops in the area of NMR spectroscopy. He is an international advisor for European School for Solid State NMR. His research interests are: Professor Madhu is interested in various aspects of NMR, both solution and solids, in particular solid state NMR. His main interest is in the methods of developed to improve sensitivity and resolution of NMR spectra. He has also contributed to the understanding of conformational aspects of amyloid peptides and their interaction with membrane systems. Currently, he is investigating in the conformational and dynamic properties of oligomers of the amyloidogenic peptides and have been proven to be toxic and responsible for many of the neuronal diseases. He is further interested in techniques to enhance the nuclear polarization. He works on the optical pumping of noble gases. He also have been investigating optical magnetometer using weak measurements methods to detect extremely low magnetic fields on the order of nano and picotesla. With all this brief introduction, over to you, sir.
Thanks. Thanks for the kind introduction, Dr. Bharadwaj. And thanks for the invitation, Dr. Ashley, for this nice workshop. It's indeed a pleasure to be a part of this. So what I'm going to do is to tell you a little bit about the nuclear magnetic resonance principles and how it is used to get into the structure and the dynamics. But I must apologize at the onset that I'm not going to get into the details of the structures and the dynamics, but I will concentrate more on the perspectives and a little bit on the principles. And solid state NMR, unfortunately, will have a very backseat in the whole lecture. It's more of a specialized topic, but I will just introduce a little bit of that, the complexities and how one can try to avoid such kind of complexities and get a high resolution spectrum. With the background, what you see is the current building of TIFR Hyderabad, which has been there for the last 3-4 years. And on the other side of the road, you can see the construction is happening of the new campus, which hopefully will be in full flow in another 2-3 years. So you're most welcome to come over there when you can travel and when things sort of ease off, actually. All right, so let's get into the details. Right. So the NMR has advanced quite considerably over the last 7 decades or something like that. It has come to a stage where it can look at a large range of molecules. And it's not necessarily the biomolecules, which are what depicted over here, but it can look into the material science, the catalytic materials, zeolites, polymers, organic molecules, for instance, and a whole range of biomolecules of various sizes from a few kilodaltons to a few hundreds of kilodaltons. And all these have been made possible through a range of, an array of methods. It could be the pulse sequence development, the physics principles. It could be the advances in the instrumentation like the magnetic fields. So what we call as a magic angle spinning, to which I will come towards the end of the talk. The better probes through which you to measure the magnetic resonance signals, and the ability to detect various kinds of nuclear spins. So all these are made possible for the scientists and others to look at a range of molecular sizes. And over here is shown a variety of such interesting molecules, disordered proteins to amyloid proteins to macromolecular assemblies. And the list doesn't end here, but this is just a snapshot of where NMR has advanced as on today. So just to get back a little bit, so this is a quotation from Richard Ernst, who got the Nobel Prize for introducing the multidimensional techniques in NMR way back in the 70s, and who got the Nobel Prize in 1991. So he sort of very forcefully says that there is no other technique that provides so much. But he doesn't say information, but he says fun. And that's the principle with which I would go ahead from here. I mean, there is indeed an information content, but for me, it's also a little bit of the scientific fun, which this technique provides in ample measures, even at this stage. So that's one of the hallmarks of NMR, which I hope I can highlight in this presentation. So this has indeed gone through various stages of development, starting right from the physics principles way back in the 40s by Bloch and Purcell. And then the chemists took over, Richard Ernst and other people. And then it slowly sort of transgressed into the biological fields by Kurt Wuthrich. And that's where the NMR is making considerable progress of late, besides the fact that it has made significant contributions to the world of magnetic resonance imaging. That's in the medicine field by Paul Ottomer and Peter Mansfeld. And all of these gentlemen have got Nobel Prizes from the 1940s to the 2000s. So just if you look at the time scale of the various spectroscopic tools, which is basically an interaction between the materials and the electromagnetic fields. So here I have plotted a range of the electromagnetic fields. And if you look carefully, the NMR is actually the very low end of the energy scale. It comes somewhere over here, which is pretty much at the bottom rung of the bottom step of the ladder of the spectroscopic fields, which clearly tells you that the energies associated with the NMR are much smaller than all the other spectroscopic techniques. Especially if you look at the X-rays or the electronic spectroscopy, NMR is several orders of magnitude lower in energy. And that has a bearing in the sense of the sensitivity. So NMR is inherently a very low sensitive technique. So it is indeed a surprise that NMR actually does or provides quite a bit of information in terms of structure, in terms of dynamics. And that is precisely because of the fact that it is very less sensitive, that the time scales or the time scale of the transition is much longer compared to, say, optics or the electronic spectroscopy, which means that the resolution content is considerably higher in the case of nuclear magnetic resonance. So the sensitivity is pretty low, but the resolution is quite high. And that means that one can look at the atomic level information content, which probably the other techniques have difficulties in looking at, although the sensitivities can be much higher. So the lack of sensitivity, I would say, is the power or the strength of nuclear magnetic resonance, and that is something which we will highlight as we go on. The other aspect which makes NMR quite stronger or the powerful is the range of applications which it can dwell on. So it can look at all possible aspects of matter, but I'm just going to concentrate mostly on solution state NMR and solid state NMR in this talk. And in the solution state, it essentially looks at the isotropic materials. It can look at the membrane kind of materials, but they are much more difficult with solution. And that's where the power of solid state NMR comes in. So in the solution NMR, mostly we look at the isotropic materials where the molecules tumble fast enough so that you can get high resolution spectral lines, some of which we will see as we go on. While on the other hand, if you look at the NMR in the solid state, there is a very wide range of materials that one can look at, the anisotropic or the inhomogeneous materials, both ordered and disordered, and they span a range of materials like the crystals, the fibrils, the glasses, and you name it, and most of those materials can be accessed through the NMR of the solid state, but the size is not a particularly limiting factor. And that is one advantage which solid state NMR has over solution NMR. And that's the same advantage which it has over the X-rays and the electron microscope and so on and so forth, although most of which are sort of complementary techniques. And we will see a little bit of comparison as we towards the end of the presentation. But one major forte of NMR, which I need to highlight, is the fact that besides the structural information, this is the niche area of NMR is actually looking at the molecular motions or the dynamics. And there's a range of dynamics, as you can see over here, from 10 to the minus 15 to about 10 to the minus 3. And there is a particular biological or chemical phenomenon which happens at these time scales, like the fluctuations, for instance, the diffusion, the rotation of the methyl groups, the aromatic rings for that matter, or the chemical exchange between the within a protein or within or among the protein conformations. So all of these happen in various time scales, and NMR is one particular technique where you can come up with a pulse sequence or a design of an experiment which can essentially look at selectively that particular time scale. And that's a power which is very, very influential and very strong enough to isolate all of these motions and get precise information on what is happening within the molecule and among the neighborhood. So that is an aspect which one has to keep in mind, and which we will highlight a couple of these examples as we go on. The beauty of NMR is for each of these time scales, there is one particular experiment. I mean, the details of the experiment don't matter at this stage. It could be a relaxation-based experiment. It could be a multidimensional based experiment. It could be an experiment which is just looking at the line width or the correlation times, or transferring the polarization or the magnetization from one nuclear spin to the other nuclear spin. So you can come up with an experiment which can look at a particular time scale, and a particular time scale, as we saw earlier, is associated with a chemical or a biological phenomenon, and that can essentially look at the processes. So that is one of the major forte or the niche area of NMR, looking at the local dynamics or the globular motions over a range of time scales. That is something which I've highlighted over here. So these time scales, as we saw earlier, can span from very slow on the range of minutes to very fast of femtosecond and even faster one. And these are some of the chemical or the molecular phenomena which happen at these time scales. And as I said in the earlier slide, one can come up with an experiment which can look at these time scales in a very selective way. And that is one major strength of nuclear magnetic resonance. The other aspect which one needs to look at is there is essentially one isotope of pretty much every element in the periodic table which is NMR active. Not every isotope is NMR active, like carbon-12 is not NMR active, as all of you know, but there's carbon-13. The natural abundance may be very low, but one can still look at it through very clever ways. So there are elements, isotopes, which are NMR active. And if you look very carefully, many of them are not spin half. I mean, spin half is something which we are commonly used to, like the hydrogens or the carbons for that matter. But there are only very few elements which are actually spin half. Most of them are actually spins greater than half. That complicate the spectrum, for instance, but they are the ones which are abundant in most of the relevant nuclear or the compounds, like the ceramics, glasses, zeolites, and catalysts. And these are the elements which we call as the quadrupole spins. Some of the common ones are lithium, sodium, oxygen for that matter, aluminium, magnesium, and so on and so forth. I mean, they're much more difficult to look at, and they're mostly looked at with solid-state NMR, which has typical line shapes. The relaxation times are very fast, so they are very broad spectrum, but there's a wealth of information buried under those spectra, which give plenty of information content on these kind of materials. And this is a research field which is still being developed. People are coming up with new techniques to look at these quadrupole spins. And that is a very fertile area with lots of applications as well. You can have spins of quantum number 1, which is deuterium or 6 lithium, to spin 3 half like 7 lithium, 23 sodium, so on and so forth. Spin 5 half like oxygen. Then there are spin 7 half, 9 half, and so on and so forth. Right. So what are the ways in which NMR has been used and is being used? So one of the things which people are still interested is to look at the nuclear spin system and understand the spin dynamics or the connection of the nuclear magnetic resonance with quantum mechanics for that matter, and develop the pulse sequences for higher sensitivity and better resolution. On the application side, of course, we use it for characterizing the structure and the dynamics of a range of materials, and also in the medical applications, which is basically the magnetic resonance imaging. And if you want to look a little bit more in detail, so these are some of the specific applications in terms of getting into the structure, the dynamics. The drug design is something which people are looking at very actively, especially in these times. And the medicine, which is either the MRI or the metabonomics, in which people come up with the markers and the diseases and see whether one can design the drugs to target those kind of markers. I mean, I won't go into very much in detail of any of this. It's just to highlight some of the possible applications of magnetic resonance. So again, so the applications range from physics to the basic principles to biology to medicines. And the applications also range a variety of industries for that matter. And the pharmaceutical industries in particular quite interested in many of these applications. So that's the one snapshot of the magnetic resonance imaging for those people. I mean, I'm sure most of you are familiar with this. So there is pretty much every part of the human body can be diagnosed with NMR, which gives a very specific three-dimensional high-resolution picture of what is happening in each of these organs. And that's extremely useful, not only to identify the markers, but also to mark the progress of the disease, and perhaps even to come up with specific molecules to target the development of such diseases. So that's a very, very widely used technique for many, to target many of these diseases for that matter. The other one, which is gaining attention of late, is the metabonomics, which is again coming up with the disease markers. And is it possible for NMR to identify such markers so that one can predict the onset of a particular disease in a set of human population in a specific region for that matter? And then the other question is to come up with drugs or molecules to target these markers and subdue them as far as the spectral signature is concerned. So that's again an area which is gaining much attention internationally. The other one is, of course, the Human Genome Project, which is to identify these DNAs. And again, that has got implications in the prediction of the diseases which a particular human being might be subjected to, which is again looking at the structural distribution of the molecules to find out the folding pathways and which molecules are responsible for which neurodegenerative disease for that matter. And can we actually find a correlation between the function dynamics and the structure of these molecules? And we believe that NMR will be a key player in this game. And again, here, the structure is one aspect, but dynamics will be the major aspect as far as I look at it. So I'm just putting one slide on the catalysis. It's not just catalysis. You can look at any particular solid materials with NMR. But I just picked up this as a specific example in which one can look at the surface phenomena of various catalyses, how they interact with various other chemical molecules to either accelerate the reactions or to get a particular compound of interest. So one can get into the local structure and the composition of the framework of the solid catalyst and even predict what kind of catalyst might be useful to get a particular reaction effective. So these are some of the important applications, and a variety of molecules can be used. So this is a particular case in which titanium has been used for the functionalization of silica surfaces, and the details have been obtained by making use of solid-state NMR. Right, so that is sort of the advertisement for nuclear magnetic resonance. So what is nuclear magnetic resonance? I mean, I apologize if many of you know all these details, but I just decided to stick to the very basics and not go too much into the details. So there are three words over here, the nuclear, which essentially is the crux of the entire technique, where we probe the nuclear spins, the unpaired nuclear spins within the nucleus of the material. So the electrons circulate the nuclear spins, and the electron paramagnetic resonance or the electron spin resonance is a technique which makes use of the circulating electrons to understand the structure, but the NMR looks at the core of the nucleus and the unpaired spins over there. It needs a magnetic field for the nucleus spins to align and behave in a nice way. And these magnetic fields are mostly superconducting magnets of late. And that is essentially the medium to manipulate the nucleus spins so that the nucleus spins are arranged in a particular direction. So this is assuming spin half, where they have a plus half and a minus half, or you can call them an up state and a ground state. And the transition will take place between these two states. And that is what we call as a resonance. And the resonance is something which has to be simulated externally by a perturbation whose frequency should match the energy difference between these two levels. And the typical frequency difference between these two levels is on the order of megahertz. So that's why the NMR magnets are typically quoted as 500 megahertz, 300 megahertz, and something like that, which is the Larmor frequency of the hydrogen spins. The carbon spins will have 1/4 of the Larmor frequency of the hydrogen spins. So the resonance is a way in which we talk to the spins in terms of the radio frequency fields, because the separation is in terms of the megahertz. And that's the language which they can understand. And the transition can then happen between these two levels. And it is that particular transition which we record as a time domain signal, which we call it as a free induction decay. And the Fourier transform of that in the frequency domain will give you the spectrum, which will contain the essential signatures of the various nucleus spins in a given molecule. So the nucleus spin, essentially, you can think of it as a magnet. And it's not a completely correct analogy, but sort of classically, one can think of that in that sense. It has got a charge, which is a classical aspect, and which has got a spin, which is a purely quantum mechanical aspect. So the complete analogy to a magnet is not totally right, but one can think of it as in that sense as a magnetization, which is produced in a magnetic field, and that is proportional to the spin quantum number. So the spin quantum number typically for hydrogen carbon is spin half. Like for sodium, as we said earlier, it is spin 3/2. And this is the strength of the magnetic field or the magnetization which is created in the magnetic field on a particular nuclear spin, which is proportional to a constant over here, which is called the gyromagnetic ratio. And that ratio determines the ease with which you can magnetize a given nuclear spin. It turns out that you can magnetize hydrogen much stronger or faster than carbon. It's on the order of a factor of 4 times. Hydrogen to nitrogen is on the order of a factor of 10 times, and so on and so forth. So this is the case of a nucleus in which one has a proton and a neutron, and the electron is actually moving around this nucleus. And the NMR basically looks at the unpaired nucleus spins in the nucleus. So this is a deuterium atom. This is an isotope of hydrogen. So that's why you have a 1 proton and 1 neutron. That's a spin 1 actually. So you have to sum up the unpaired spin. So this is spin 1. If you had the hydrogen, the normal hydrogen, so that will be spin half. And here you have 1 electron, which is circulating around the nucleus. So the spin, as you know, is a fundamental property. It's essentially quantum mechanical. There is no classical analog in that sense. And it is just like a charge and a mass. And NMR makes use of the properties of the nucleus spins to understand what's going on as far as the structure is concerned. And the dynamics matters. So you can have also like the helium atom, for instance, here. So you have 2 neutrons and 2 protons. So the net nucleus spin in this particular case is 0. And this is for helium-4. Helium-3 will have a spin half, but this particular one is NMR non-observable. But the good thing is there will be 1 isotope here or there. It may be very naturally less abundant, which will have a nucleus spin, which is spin half. And the nucleus spin in the presence of a magnetic field, so that's the superconducting field, essentially goes around the magnetic field with the Larmor frequency. So that frequency is called the Larmor frequency, which is on the order of several megahertz. So if you have a magnetic field of 2 Tesla, you get a Larmor frequency for hydrogen, which is 100 megahertz. So that's the typical values of the energy separation of a spin half hydrogen in a magnetic field of 2 Tesla for that matter. And this is, again, in a classical analog, is like a spin gyroscope in a gravitational field. Although, again, one has to be careful that the spin really doesn't have any classical analog. So this is how you can pictorially represent a spin half in a magnetic field, where the nuclear spin is precessing around the magnetic field with the Nmr frequency. And there is an energy separation between the two levels of the spin half. There's a plus half level and a minus half level. They are degenerate in the absence of a magnetic field. But the moment you switch on the magnetic field, which we call as the Zeeman effect, the separation happens. And the separation keeps increasing as you keep increasing the magnetic field. So that's why people love to go to higher and higher magnetic fields, because here the transition frequencies are more energetic or much stronger. So if you do the NMR at this particular magnetic field, the sensitivity issues become much more worse in this particular case, while here you have much higher sensitivity compared to the lower magnetic fields. I mean, you pay a high price in terms of the cost, but you gain in terms of sensitivity, also in resolution as you go higher in the magnetic fields. And once you have the energy level splitting at a given magnetic field, you apply the radio frequency waves. So these are the radio frequency waves, which causes the transition between the plus half and the minus half. And that, once you switch off the radio frequency field, this particular population difference can be picked up by an oscilloscope as a time domain signal, and which can be Fourier transformed to get a spectrum. Now, this is all fine as far as the nuclear spin is concerned, but the nuclear spin by itself is not going to give any information whatsoever unless you have interactions, you have local interactions through which the spins can probe the medium. I mean, the spins are there, the molecular structure is there. There should be some connection between the spins and the medium, and that is given by various spin interactions. The NMR is lucky enough to have a large number of interactions. The common ones, as some of you might know, are the chemical shift, which essentially made NMR very useful to get piecewise assignment information. You have and this is a single spin interaction, which is actually caused by the external electrons, which are revolving around each of the functional groups of a particular molecule. You can have the dipole couplings, which is a through space mediated interaction. This is very important for structural information because it carries the distance between the two nuclear spins and also the torsional anchors. Then you can have the through bond couplings. I mean, you heard a lot of the bond information yesterday when Arun was talking about hydrogen bonds and so on and so forth. And that's a bond information that we can pick up quite easily, which is mediated, which is an indirect magnetic interaction between the two nuclear spins, mediated through the surrounding electronic cloud, which is the scalar, the scalar coupling, or the through bond, the 1 bond, 2 bond, 3 bond couplings. And that's again very important because it gives you the bond angles, again the torsional angles, whether the molecule is in an alpha sheet or beta helix and so on and so forth. And then the quadrupole couplings, as I said earlier on, which also give you a lot of information about the structure and the dynamics. So these are some of the prominent interactions. There are many more other interactions. The prominent interactions are these which help us in getting the structure. In the solution NMR, unfortunately, this interaction and this one is completely averaged out because they carry the spatial information, or rather the anisotrope information. And the anisotrope is completely averaged to 0 in solution because of the rapid tumbling of the molecules, the Brownian motion, which is good for resolution. And that's why the solution NMR are normally give you very sharp lines, because you only have the isotropic chemical shift and the isotropic bond couplings. You don't have anything coming from the dipole or the quadrupole. The price you pay is that getting the structure information is much more difficult in solution. But in solid state, you have all this information present, which means the resolution is poor, but the information content is enormous. So the question is always, what do you want? And then can I get what I want in a very clever way? And it turns out that you can actually have the cake and eat it as well. It's quite a bizarre kind of a technique, which has its intrinsic problems. One can come up with spin physics to overcome all of these. So if you look at the spin interactions a little bit more in detail, we have what we call as the external interactions, which is the Zeeman magnetic field, the superconducting magnetic field, and the radio frequency field, which is time dependent. And then you have the internal spin interactions, as we saw earlier. The isotropic parts, which are the leftovers after the molecular tumbling has happened, are time independent. So they are easy to handle. The anisotropic parts, which have the orientation information, like the dipole-dipole coupling or the quadrupole coupling, they have the information about the distances and the angles. They cause the line broadening. They have plenty of information, and they are time dependent in most of the cases. So theoretically handling them is much more difficult. There are tools to do that. The internal spin interactions can be further classified into a magnetic interaction. So the chemical shift, the couplings are all magnetic interactions, while the quadrupole interaction is actually caused by the gradient of the electric field. And that's a much stronger interaction. Most of these interactions are in the range of hertz to kilohertz, while the quadrupole interaction can go up to megahertz to even gigahertz, actually. So that's a very nasty interaction in that sense. The nuclear spin interactions, most of the times when you do solution NMR, you're only worried about the chemical shift, and even in the chemical shift, only the isotropic part, because the rest everything is averaged to zero, and that is which determines the fine structure, which basically comes from this scalar couplings, the splittings, and so on and so forth. And we will see some of these examples as we go on. The anisotropic parts are actually there, in fact, and they contribute to the relaxation, which is even more complicated topic. So I won't go into the details of that. If there are some questions, I can try to answer that later on. So relaxation is very important as far as spectroscopy is concerned, and for NMR in specifically, and that is caused by these anisotropic orientation dependent phenomena. So as I said earlier, in most of these cases, the anisotropic interactions are all gone to zero by rapid molecular tumbling in solution NMR. In solid state, they are not actually. So we have to find out ways to remove these anisotropic interactions in solid state. But they do contain a lot of direct information, and they are particularly useful to get structures and dynamics. Some examples of which we will see as we go on. So that's the aspect about the nuclear spins and the external magnetic field, which is actually caused by the superconducting magnets. So that is one of the very old examples of a superconducting magnets. The magnets have advanced much ahead these days. They look much more compact of late. So that's the superconducting magnet and the console, which essentially consists of the pulse generators, amplifiers, preamplifiers, digitizers, and so on and so forth. And then you have the probe in which the sample sits. The probe essentially is an inductance capacitance circuit in which you can tune the probe to the particular nuclear spin that you want to look at. And then there are ways in which you can pump in air to control the temperatures or to spin the sample to get a little bit more higher resolution for that matter. And the coaxial cables to pump in radio frequency pulses. And the coil sits over here, and the sample sits inside that coil. And this whole probe goes under the magnet, and that is the configuration of the superconducting magnet. So you have a helium jacket, which is sitting inside the superconducting magnet, which is surrounded by a liquid nitrogen jacket, which essentially keeps the magnet cool, perpetually cool. And that is a perpetual magnet which keeps on going once it is charged. So whatever I said in a nutshell is depicted over here. So you have a nuclear spin contained in a molecule which is kept inside a magnet in a probe. It has a precision frequency which is given as the Lambda frequency. In terms of the magnetic field, it is gamma times B naught. So the gamma times B naught is in frequency units, so that's why it is the frequency, the Lambda frequencies, and that is the resonance, which we measure by applying a radio frequency pulse. The Fourier transform gives the NMR spectrum. Inside the console, we have the following deals. So we have the spectrometer, which has again the magnet, the probe, and the sample, which is sitting inside. The pulses are generated as a co-sinusoidal waves. And this is what we call as a 90-degree pulse, 180-degree pulse. It can be more complicated. And the receiver basically collects the signal once the radio frequency signal is switched off. And that's a decaying magnetization signal because the relaxation takes over and the signal decays. It decays faster if the relaxation is fast enough. It decays slower if the relaxation is slow enough. And if the relaxation time is slower, the line widths are much sharper. If the relaxation times are shorter, the lines are broader, which is what happens in the case of the solids. And this can be Fourier transformed and one can get information of the response of each of the functional groups in a given molecule. So that is essentially what the NMR does. And just a bit of information on the development, what we had in the superconducting magnet. So way back in the 60s, people were talking about 60 megahertz magnet. And now we have reached a stage in which we are looking at 1.2 gigahertz magnet. I mean, that's a tremendous advancement. The major aspect in the design of the magnet is actually the superconducting coils, to come up with a particular design of a coil which is not brittle, which can be wound to produce a very highly homogeneous magnetic field, essential for the NMR purposes. And right now we have magnetic field which can go up to, which can give alarm frequency for the hydrogen as 1.2 gigahertz. Of course, the price you pay for that will be like 100 crores or something, but the magnets are available these days. So TIAFA Hyderabad is now planning to look at a 900 megahertz magnet, which is already quite a substantial amount of investment. But in terms of resolution, sensitivity, and dispersion, it's actually worth the investment in that sense. Right, so that's in a nutshell that we have talked about the nuclear spins in a magnetic field, the energy level splitting, the RF causing the transition. And that causes, once we switch off the magnetic field, whatever RF the nuclear spins have absorbed, they emit the RF field out, which is picked up by the solenoid coil. And that's picked up signal is essentially a co-sinusoidal time-dependent signal in the oscilloscope, and the Fourier transform gives rise to the spectrum. So that's in a nutshell what NMR is all about. The rest is actually the detail. If you know this much, one can actually carry out the experiments. So these are some typical nuclear magnetic resonance spectra. So this is a spectrum of some particular molecule of looking at the hydrogens, the protons as we call it. You can also call it the carbon-13. You can see that there's one major difference you can see over here is the labels on the exact. In hydrogen, it goes from something like 0 to 10. In carbon, it goes from 0 to 270 or even 300 ppm. That has its own significance, actually. So the carbons are much more dispersed in nature. You can have a resolution which is more in carbon because of the high dispersion in the chemical shift. So this is actually a chemical shift axis, which is a frequency, which is a dimensionless axis, and I will come to it in a minute or so. So what's the information content that we can get? We know that the energy is given H2, and we're looking at very low energy range as we talked a bit in of the presentation. So we are sitting somewhere over here, while the most sensitive spectroscopic techniques are sitting over here, but still we have plenty of observations. So what we look at could be the peak position, which is what we call as a chemical shift, and that can be quantified as some kind of a chemical shift index, and I will define that in a minute. And the information which it has is a chemical environment of the nucleus, the functional groups, and what all is there around a CH3 group or a CH2 group. One can look at the splitting of the resonances, which gives rise to the information about the coupling constant. So the separation between the two peaks is directly proportional, is directly equal to the coupling constant, the 1 bond, 2 bond, and that tells me about the peak separation or the intensity ratios, which gives me an idea about what kind of nuclear spins could be at the neighbor, and more importantly, a measure of the torsional angles. One can look at the peak intensity, which is the integral. You integrate the peaks, so you find out the area under the curve, and that gives me the relative height or the population of that particular functional group or the nuclear spins, and that's the nuclear count. You can look at the peak shape also, the line width, which is 1 over the transverse relaxation time, and that's a very good indicator of the molecular motion or the chemical exchange. So these are the observables as far as NMR is concerned in the first go. There are much more than this, but this is something which one can do in a very simple spectroscopy. And you can see that already there is a plenty of information content over here concerning the structure, concerning the dynamics, and concerning the geometry in terms of the torsional angles. So that's the strength of the nuclear magnetic resonance. And as people know that what made NMR quite interesting and useful is the ability to distinguish each functional group in a very clear way. So if all the protons or if all the hydrogens were the same, simple molecule like ethyl alcohol, I mean, one would just get one resonance. And then, of course, it is boring. I mean, you can calculate the movement of hydrogen, but you won't be able to identify the functional groups or get the structure. But it turns out that each of these functional groups has a different electronic environment, the hybridization for that matter. And that gives rise to 3 different resonances with 3 different intensities. Now, this is just a schematic, but this is perhaps the actual spectrum with even the line splitting. And the lines are split because of the scalar coupling between each of these functional groups. And we will come to it a little bit more detail. So this chemical shift is because of the electronic environment, these green dots around the nuclear spin. And that is different for different functional groups. So although the bulk Larmor frequency is the same for every hydrogen, there is a slight deviation from the main Larmor frequency because of the field which is induced by the moving electrons. The moving electron also causes field, and that's a field which is opposing the static superconducting field. So the effective field which the nuclear spin C will be the B naught minus the field which is induced by this electron. And that's why you get a difference in the Larmor frequency for the same hydrogen spin, but depending upon which functional group to which it is attached. And that makes NMR very powerful. And this particular interaction is called the chemical shift. So that's again the ethyl alcohol spectrum. And it turns out that the idea of chemical shift was first suggested by an Indian scientist, Hermati, who was working with Felix Bloch in Stanford University. In fact, the physicists were not very convinced with the chemical shift. So they actually, they call it like a chemical shift without realizing the significance of it. And they moved to what they thought were more promising lines of research. But Hermati was very clever, and he pointed out that this is indeed a universal effect, that a simple organic compound would show several proton resonance frequencies. And that became the history. That became the most useful aspect as far as chemistry is concerned, and also for the assignment of proteins and so on and so forth. And it's interesting that Packard, who was one of the co-authors of the first paper on chemical shift, remarked that he had never really believed the structural formulae written by chemists until he saw the ethanol spectrum. So he never believed that it actually had a CH3, CH2, NOH. But once you look at the NMR spectrum, that's rather clear, in fact. And that's the powerful one. Hermati actually joined TIFR and started the NMR group there. So that is Professor Hermati. And this is, of course, Homi Bhabha and Jawaharlal Nehru. I think they were inaugurating the workshop in TIFR way back in the mid-50s, actually. Right, so NMR has come a long way since then. The chemical shift invention, which was in 1949 or so, and NMR by itself was invented in 46. It has seen several developments. The Fourier transform, which came in the 60s by Richard Ernst, and the multidimensional techniques, which really transformed the way one did NMR. Again, the main contributor was Richard Ernst, and then the applications to the proteins by Kurtwuthriek, and then a variety of techniques by which people have extended the application of NMR to larger and larger macromolecules. Just from my own point of view, I've highlighted here a little bit of the developments which people have made in the field of solid-state NMR, which started along with solution, but it lagged behind because of the lack of resolution. The clear resolution started sometime in the early 2000s when people started coming up with very, very efficient pulse sequences and extending the applications of solid-state NMR to the biomolecular applications. It has seen a range of applications, starting with very broad signals to getting back to sharp lines. So here you can see one of the early spectrum of adamantane carbon-13 was just a noise. There was nothing there. And at some point, people could make out a very broad carbon-13 spectrum. And only in the 80s, one could actually distinguish the two carbons, the CH2, CH peaks, on the order of 2 hertz or 3 hertz line width. So these developments have been happening in both solution and solids. And solids, the developments are still happening because there are still quite a few challenges. One or two of them will mention as we go on. Let's just get back to the solution state in the chemical shift. So again, as I said earlier, this is because of the local induced magnetic field by the circulating electrons around the nucleus. And that's the reason why we see distinct NMR peaks for each of those functional groups. And the shielding depends upon the electron density, and it depends on the structure of the compound. So the normal nomenclature which you might see in the old books is the high field and the low field, which I think are technically wrong. One should clearly talk about the de-shielding or the shielding regimes of the chemical shift. But that's more a question of semantics. So again, this is another example of an organic molecule where one can see different distinct peaks for distinct hydrogens or the protons. Right. So in NMR, we don't actually measure the exact resonance position because that's a relative one. So we measure how far de-shielded it is from the tetramethylsilane, which is the reference compound. So that doesn't interact with most of the other molecules of interest. And all the hydrogens in this particular compound appear at one position. They are all equivalent. And one actually measures the shift in hertz of the hydrogen of interest with respect to a reference peak. And that's what we call as the chemical shift. It's a dimensionless unit, which is a relative unit, as a matter of fact. And it is important because that is independent of the spectrometer that you use. So if I say that something comes at 1 ppm, it comes at 1 ppm, independent of the spectrometer that you use. So the hertz depends on the frequency, but the chemical shift does not depend. But on the other hand, the higher frequencies also means that you have a larger shifts as far as if you talk in terms of the hertz. So that's something which one has to keep in mind, which has some bearing when you go to the scalar coupling measurements. So if I look at the operating frequencies, people say that 500 megahertz, which means the hertz equivalent of ppm is actually, so 1 ppm is 500 hertz. And this is with reference to the hydrogen atom. If you're talking about the carbon spins, this will be 1 ppm will be 125 hertz. If you talk about nitrogen 15, that will be 10 times smaller than this. So 1 ppm will be 50 hertz. So that's the connection between the frequencies and the ppm in this particular case, talking about the protons or the hydrogens. So the chemical shift index, which we call as the delta, is defined as a shift divided by the spectrometer frequency. So that's dimensionless. So that's 1 part in a million. So this is 1 hertz and this is megahertz. So that's why this is called parts in a million. And higher frequency, as I said earlier, one can see that it leads to more dispersion. So 10 ppm will cover 500 hertz for hydrogen in 500 megahertz, while that will cover 6,000 hertz in 600 megahertz spectrometer, and so on and so forth. So you get a higher dispersion as you go to higher magnetic fields, plus the higher sensitivity as well. And the chemists have made all kinds of charts for easy assignment of standard molecules for that matter. So where does an aliphatic proton come in? Olefins, aldehydes. Similar patterns have been made for the carbons and the nitrogen. So these tables are widely available, which people can look at. And these are, again, some of those representative positions in which many of these functional groups might appear in the proton spectrum in this particular case. So the chemical shift is also, I mean, there's nothing sacrosanct about the chemical shift. It is also decided by the electronegative elements, by the pi bonded. And as most of you would have seen yesterday in Arun's talk, the hydrogen bonding can also make it de-shielded in many cases. So I just have a couple of examples over here. So if I have the halogens, for instance, the electronegative element, that can actually de-shield the proton if you look at the hydrogen spectrum. It takes the valence electron density from the carbon, and that can make more density for the hydrogen, de-shielding that particular hydrogen spin. So the hydrogen spectrum would come much more de-shielded if you have more of these electronegative atoms. So it depends upon the kind of the electronegative spin, and it also depends upon the distance between the hydrogen and that particular halogen in this case. So if I have like fluorine, oxygen, fluorine, each of them has different electronegativity, and depending upon the electronegativity, the shielding also will be different. Larger the negativity, the larger will be the de-shielding. So in this case, it is the maximum for the fluorine, and the minimum in this case for tetramethylsilane, where there is no shielding, no de-shielding whatsoever. So it depends on the electronegativity. It also depends upon the number of such electronegative atoms. If I have 3 of these, it will have more de-shielded. And it also depends upon the distance. So if I have just a CH2Br, it is much more de-shielded than having a CH2, CH2b, where the distance between this and this is much longer. So all these aspects come into being. It also says that by looking at these chemical shifts or the de-shielding, I can also already predict what's the kind of surrounding the electronic atmosphere, or what's the kind of the atom which is sitting close to the hydrogen that is being observed. It also depends upon the pi bonds, which cause the anisotropic fields, the magnetic fields, which also can affect the chemical shift through the ring current, which is an induced effect, which also will have the de-shielding. And of course, the benzene rings will have the greatest effect in this case. So this is the case. This is an example in which I have the ring protons coming at 7.3 instead of 5.6 in cyclohexane because of the circulating charges around the nuclear spins. So these again causes secondary magnetic fields, just like the circulating electronic clouds in the normal atmosphere. And it also depends upon the hydrogen bonding. So the stronger the hydrogen bonding, the de-shielded, again, the spectra would be. The carboxylic acids have strong hydrogen bondings, and they form dimers, as we saw yesterday. And that also will have a largely down-shielded hydrogen spectrum. The alcohols also will vary in chemical shift from, as you can see, from 0.5 ppm, which is without the hydrogen bond, to about 5 ppm, which is lots of the hydrogen bonding. So that can lengthen the hydrogen bond. It can reduce subsequently the valence electron density and gets de-shielded the spectra. So that's one example over here, where there is no de-shielding, where there is no hydrogen bonding. And the moment you have the hydrogen bonding, you can go several ppm de-shielded. The other major thing which the solution NMR people are concerned with is the spin splitting, which is a consequence of the scalar coupling or the through bond interactions. There is nothing spatial over here. It's essentially a chemical phenomenon mediated between the two nuclear spins by the surrounding electron cloud. And that's the famous N+1 rule. So each line will get split into finer structure, a doublet or a triplet, depending upon how many number of such nuclear spins are in the neighborhood. So this is essentially mediated by the Fermi contact between the two nuclear spins. And the interesting thing is the splitting is important to get an idea about the coupling constant. But more than that, it gives rise to a number of physical properties such as hybridization, the dihedral bond angles, and the electronegativity. All can be measured by looking at these split properties. So these bond angles actually follow the Karplus relations. So you can fit the variation in the two bond couplings or the three bond couplings to the Karplus relation, from which I can get an idea about the bond angles and the torsion angles. And this in turn can be mapped on the Ramachandran map. And I can say which region of the Ramachandran map my torsion angles of the specific molecule would be fitting in. So it could be either over here, if it is fitting over here, it's a beta sheet. If it is over here, it's a right-handed alpha helix or a left-handed alpha helix or unstructured molecule, if it is not fitting into any of these. So this already tells me an idea about the secondary structural element of the biomolecule by measuring the coupling constants and fitting that with respect to the Ramachandran map. So this is how the N+1 rule works out. So if I'm looking at a CH spectrum over here, which is coupled to a CH2, then I get, so this particular one would be split into N+1, which will be 3 lines because it is coupled to 2 hydrogens. And this by itself will be split into a triplet because it is coupled to, a doublet because it is coupled to an hydrogen over here, and so on and so forth. So here there are some of these patterns. So I have a CH, each of which is a doublet. If I have a CH2CH, so this will become a triplet, while this becomes a doublet, and so on and so forth. So you can have very complicated structures, a split pattern over here in this kind of a moiety. And these are the things which one can observe very clearly in NMR. And when you measure the peak splitting, I can get an idea about the coupling constants. And as I said earlier, about the angles as well. So the coupling constant is actually the measure of the distance between the split patterns. And it is also a strength of the interaction between the two sets of hydrogens, which constitute that multiple. So these are some typical values, which most of you might know. One can look at the 3-bond to 2-bond or a single bond couplings. So it depends upon which kind of nuclear spins are looking at. So these are essentially of the hydrogen-hydrogen. If I look at the hydrogen-carbon, it could be like 120 hertz to 200 hertz of that order. and also similarly for carbon-carbon and so on and so forth. The J couplings, it's not just the idea of getting the coupling constant. So J coupling is also essentially a very powerful way to transfer the magnetization from one nuclear spin, say hydrogen, to another nuclear spin like the carbons. And that is essential in multinuclear experiments to get the correlation experiments between hydrogens and the carbons. We will see at least one example towards the end of the talk. Now, the coupling constants, as you know, are constant, so they don't depend on the magnetic field. The chemical shift, you could see that there is a dispersion, but the coupling constants are just constant. They don't depend on the magnetic field. However, as you increase the magnetic field, because the chemical shift, there is a dispersion. As you can see over here, these look a little bit more farther separated out here. So the constant is 7.5 over here, whether it is 200 megahertz or whether it is 100 megahertz or 200 megahertz, but the separation looks larger because the dispersion is larger because of the chemical shift. To highlight this a little bit more, and that's the reason why people insist on higher magnetic fields. If you plot, so in the slide earlier, actually I was cheating a little bit. So this is 6 ppm and this is 3 ppm. If you plot both of them on the same scale, they look compressed. Right? The chemical shift, of course, is a dispersion, but the coupling constant is compressed, but this distance is 7.5. This is also 7.5. But as the chemical shift has gone larger, the split pattern looks a bit compressed, although the distance is the same. Now, this is actually advantageous, and the reason is given over here. So why buy a higher field instrument and pay much more money? If I look at a 50 megahertz and for some typical organic molecule, if the coupling constant is 7.5, and if I have 3 functional groups, a brown one, a green one, and a blue one, this is how it looks like. And unless I color code it, and I don't think I can color code it in a molecule, I mean, I really don't know which is green, which is blue, which is brown. So all of them look like belonging to each one. So there is no way I can measure the coupling constant here. If I go to 100 megahertz, it gets a little bit better. And this is because of the chemical shift dispersion. The coupling constants are again constant, but the dispersion is changing. But still, there are overlapping lines, so you can't separate out the multiplet. But then now you go to a higher field, 200 megahertz, the split patterns are exactly fantastic. I know that the blue lines over here, the green multiplet is here, and the brown multiplet is here, and I can measure the coupling constant very well. I know which is which. Assignments are done very well. And this is even more important for protein molecules where the crowding is much larger. And that's why people want to go to 800, 900, 1 gigahertz, and so on and so forth. So in the last little bit of 5-6 minutes, I will highlight the complexities of solid-state NMR. I won't go into the solution of it. The advantages of solid-state NMR compared with solution NMR are the fact that the information content is quite abundant. The resolution is practically 0 because the lines are very broad because of the presence of the interactions. So one has to come up with artificial ways to induce the resolution. And one of them we do is a sample rotation. As you remember, the resolution is high in solution because of the rapid tumbling of the nuclear spins. So the question we asked ourselves is, can we induce a Brownian motion within the crystallites in a given powder in the solid state sample? So you have to rotate the sample. Now the question is, at which angle do you rotate? And that's very important, and that's something which I will come to in a minute. But there are many other advantages of solid state. So one is I can generate any symmetry that I need, unlike in the case of the solution, because I have the complete control of the Hamiltonians. I can generate external symmetries. I can generate the internal and dynamic symmetries because the whole process of sample rotation is time dependent, actually. I suppose that's not a question. Yeah. All right. So there are many proteins which cannot be looked at by conventional solution NMR, like the globular proteins, the assemblies. They're not just soluble. Membranes are not soluble, mostly. Fibrils or oligomers. So they can only be looked at by solid-state NMR. So there is a need for solid-state NMR. It is difficult, but there's a need for it because most of the materials that we are interested in, and also the glassy materials, many catalysts, many polymers, they're not soluble at all. The solution NMR has a size limitation, very narrow resonance, so that's advantage. Solid-state NMR has no size limitation, but the resonances are very broad. So how do I tackle them? So I will just address the question of, so that's the difficulty. So in liquids, you get sharp line. If I get a single crystal, also you get a sharp line. But if I get a powder, which is a solid state sample, you get a superposition of this single crystal spectrum, which is a broad line. It has a typical shape, and that shape depends upon what we call as the properties of the tensor associated with it, which already has information content. But this is only for one spin. But if I have an organic molecule, even for a small organic molecule, you get an overlap of several of these, and that just gives you a featureless Gaussian line. And that is useless. So the question is, can I go from here to here without sacrificing the information content? And that's the whole beauty of the pulse sequence design. So again, to highlight the difficulties, this is a proton spectrum of a protein sample of about 100 residues, very nicely resolved. And this is just a carbon-13 spectrum of glycine, just one amino acid, and that's already a very bad spectrum. So can I get a good resolution in the solid state? Which means that I have to mimic artificially the Brownian motion in solid state. That gives rise to resolution, which is what we call as decoupling. But at the same time, can I get the anisotropy? Because that's the strength of solid state NMR, that there is direct information content there, which is, can I get it back even if I get the resolution? And it turns out that I can do that, and that's something which we call as the recoupling, which I won't go into the detail. So essentially, I have a powder spectrum, which is the superposition of all the crystallized. So that's a typical powder line shape. And can I narrow it down? And this powder line shape can be from the chemical shift anisotropy in this particular case. Earlier, we were only looking at the isotropic chemical shift, but we do have the chemical shift anisotropy. We have the anisotropic dipole-dipole coupling between the two nucleus spins. It has the distance dependence, it has the angular dependence, which can broaden the line. You can also have the anisotropic scalar coupling, which can also broaden the line besides splitting. Now, the way to remove all this anisotropic interaction and to get sharp line is what we call as the magic angle spinning. So we have to spin the sample to mimic the Brownian motion, and the angle at which the sample is spun is at an angle of 54.7 between the sample holder and the magnetic field. So if you look at the normal solution probe, the sample sits parallel to the magnetic field, but here it sits at an angle of 54.7. Now you can ask the question as to why 54.7. So I won't tell you all the details. It turns out that all these anisotropic interactions are rank 2 in nature. So these are tensors of rank 2. And any rank 2 tensor will transform like a second rank Legendre polynomial upon rotation. And every second rank Legendre polynomial has an overall 3 cos square theta minus 1 multiplying it. And the 3 cos square theta minus 1 will go to 0 when theta is 54.7. So that's in a nutshell, that's the principle why we choose the angle of 54.7. And that's the magic angle. So that's called the magic angle spinning. So you remember the spectrum of the carbon-13 of glycine molecule, which is very broad, no spinning. The moment I do the magic angle spinning at 12 kilohertz, it's actually a very fast spinning if you look at it. You get sharp lines. This is still not as sharp a solution. This is still about 50 hertz. In solution, you get about 1 to 2 hertz. But this is about thousands of hertz, and you're already getting down to 50 hertz, which is considerably fantastic. And these days, you can spin much faster, and I will show one slide of that, in which I can get this to about 10 hertz or 5 hertz, as a matter of fact. So this is the reality. So this is the static spectrum without spinning of glycine. So that's the CH2 peak of the glycine. That's the carbonyl COOH. That's a broad spectrum. That's a relatively narrow, but still several thousands of hertz. And as you keep spinning, the resolution increases. The anisotropy is contained in what we call as the side bands, from which I can get back the information content of the geometry as well. So that is something which we call as the magic angle spinning. There are different sample holders of different sizes. Depending upon the size, you can get larger and larger spinning frequencies. So these are big rotors, which the maximum speed will be about 5 kilohertz, 7 kilohertz. This can go up to 15 kilohertz. This goes up to about 25, 3.2 millimeter, which is the diameter of the rotor. This is 2.5 millimeters. You can see that's a very small rotor. This is compared to 1 cent of the Canadian currency. And this is 1.3, which I myself cannot even see that physically. And that you can spin up to 60 kilohertz, which is a very fast spinning. And these days you can even have 0.8 or 0.7 millimeter rotor, which you can spin up to 100 kilohertz. So just for some stat, this is something like one of the highest frequency man-made mechanical device. So this is a 250 meters per second. And if you do that, it takes about 44 hours to go around the whole Earth. It's an incredibly fast spinning if you look into that. And the one which we have in TFR is a 0.7 millimeter, which I really can't see at all physically. And you can see that this one, the proton spectrum of adamantane, which is normally a broad line. Now I actually can see the two protons. They actually have two distinct protons split at 7 hertz. And you can see that by spinning at 111 kilohertz. And that's really an incredibly high speed. Of course, it requires a tremendous amount of sample preparation to get the sample into this particular rotor is an extremely difficult task. But once you do that, you can get higher resolution quite well. I have a couple of slides on the dynamics. So one can look at all this, the dynamics as well, both in the solution state and solid state, by looking at the line shapes, the exchange phenomena, either you have a two-site exchange or intermediate or a fast exchange, and so on and so forth. I can also look at the line shapes of deuterium or oxygen. Even though they are a broad spectrum, the characteristic line shapes will tell me what's the kind of dynamics that is happening. And you can also extend the one-dimensional spectroscopy to two-dimensional or multi-dimensional spectroscopy. So this is what I have been doing so far, a pulse and collecting the signal. But I can do that, so that is good enough. But if I have a complicated spectrum, it is very difficult to assign such a spectrum with the one-dimensional spectroscopy. So you need to correlate these particular resonances to understand who is talking to, which functional group is talking to, which other functional group. And the way to do that is something called a two-dimensional spectroscopy introduced by Chenet and Richard Ernst, in which instead of one pulse, I apply a second pulse as well in the simplest way. I mean, it could be more complicated. And there is a time increment over here. And that's the standard free induction decay. So I have two time domains. Subsequently, I have two Fourier transforms, and that gives me a two-dimensional spectroscopy. This is how the multiple dimensions are created in NMR. So I Fourier transform with respect to the normal time, and then I Fourier transform with respect to this particular time scale as well. And the advantage of this is something which I'll show you in a minute. So if I take an ethanol spectrum, which is a relatively simple molecule, one look of which I can identify each of these functional groups. But for a more complicated molecule, I need to see which functional group is talking to which other functional group to understand the coupling between both of them or the distance between both of them. So this is what I get in the normal one-dimensional spectrum. So that's the CH2, the OH, and the CH3. But if I do the two-dimensional spectroscopy, this is what I get. So this is what I call the diagonal peaks, which are not interesting. That's already here. But then I get the cross peaks. So there is a cross peak between CH3 and CH2. And the strength of these will tell me the distance between them or the coupling constant between them, which will be useful for more complicated molecules. For ether alcohol, of course, you can get it by looking at the 1T spectrum. But the correlations can be built up for a complicated molecule by doing multidimensional spectroscopy. So here, there is a correlation from the CH2 and the OH, and these are the correlated peaks, the strength of which tells me something about the proximity. And that's the CH3OH. That's the advantage of doing the multidimensional spectroscopy, which has helped NMR in getting into the multidimensional structures of proteins and a large range of molecules, looking at the protein function, structure, dynamics paradigm. So I will skip this part. I mean, one can look at the biomolecular NMR, in which one of the main characteristics is look at the structure and the dynamics and get complementary information from X-ray and electron microscopy. Of course, one has to prepare the sample, do the experiment to get the assignments, then the secondary structure from the chemical shift and the scalar couplings. From the dipole coupling, you measure the distances, and then you fit all of them into into a molecular and a program to calculate the minimum structure calculations. So that's where the future lies in, to get a clever design of our sequences, higher magnetic fields, better probes. And all of these will help us to get in line with this fundamental question which people are asking in the protein folding, for that matter, or in material science. So just to summarize my talk, so this is, people ask this question as to how these techniques compare with. I wouldn't compare any of them. I would just say that each one of them has its own niche areas, and each of these techniques complement very nicely each other in many different ways. One can also look at the relaxation aspects, which I did not talk about, either the transverse relaxation time or the longitudinal relaxation time, and that also gives an idea about the internal mobility or the conformational exchange. So I finished with this. So these are the major interactions that we talked about, either in liquids or in solids. So this is how they affect the liquid and the solid. The dependence of each of this interaction on the magnetic field, and what each of these interactions will actually give you in terms of the structure and in terms of the dynamics, and how they manifest in either in the solution state or in the solid state. So that's a summary of what I essentially talked about. So the future, of course, is promising. So one of the things which we try to do is to improve the sensitivity of nuclear magnetic resonance. Metabonomics, as I said, and as the sensitivity increases, one can look at in-cell NMR, where in vivo one should be able to look at these proteins, the biomolecules, or look at the surfaces of materials like catalysts, zeolites. So these are very less sensitive, but with the advancement in the methodologies, one can probably look at. On the physics side, people are interested in quantum computation, and we are also interested in not just high field, but zero field is also interesting, because that carries more information than high field. It looks a little bit oxymoronic, but that indeed is the case. And that is a new field which has come up in NMR, which we are also trying to look at. Thanks for attention. I stop here. Actually, I'm done.
Yeah, yes, sir. Yes, sir. So thank you, sir, for the informative sessions. Participants, you can raise your questions here. You can unmute yourself and ask questions. Sir, I have a doubt. So what are the nuclei we can study using a solid state NMR?
So you tell me which one you want. Everything. So as I said, pretty much all the elements of the periodic table, all of them are NMR active.
Okay.
And they can look there. In fact, there are more nuclear spins amenable to solid state than the solution state, because if you look at some of these materials, they only exist in the solid state. They don't exist in the solution. Many of the polymers, for that matter, I mean, they're not soluble. So you have to use solid state. But you can look at any nuclear spin. So some of the common spins which are useful will be sodium, oxygen, aluminum, magnesium, for that matter. Besides, of course, the nitrogen, carbon, hydrogen.
So actually, we look for
hydrogens very, very rarely, because hydrogen-hydrogen dipole coupling is very, very strong. So that is something which we have started looking at only recently. So we look at the other nuclear spins, which contain more information.
Okay, so normally we look for the isotopes, right? So the ratio of isotopes.
One of the isotopes, like oxygen, if you look at it, it will be oxygen 17.
Okay,
so the price you pay, sensitivity will be lower, because oxygen 17 is low sensitivity. So you have to label them in most cases. Or you have to come up with techniques by which you transfer the magnetization from hydrogen to oxygen, which is another one which we are trying to develop our sequences for that. Yeah, so that's again a research area which is very active. Okay. But if you look at sodium or lithium, they are 100% abundant. 7 lithium or 23 sodium, that's 100%. One can look at nitrogen 14, which is spin 1, that's 100%, is much better than nitrogen 15 in that sense. And that's again, people are trying to look.
Sir, I'm Vijay Kumar Reddy here. Hello, sir.
Somebody has a question, how do you put sample in this small spinning rotor? I have never put that myself in because I can't see those rotors anyway. So the way to do that is, so you're provided with a microscope by which you can amplify the rotor, and you essentially have a small centrifuge, and you actually centrifuge the whole powder inside into the rotor. The big rotors, you can actually fill it manually. That's pretty straightforward. But the small rotor, you have to connect it with the centrifuge, and you have to automatically centrifuge in the sample. So that's a very delicate process. So, these rotors are also fragile. So if you do it in the wrong way, you can break the rotor, and then you lose 3,000 euros straight away. So you have to do that in a very clever way, so you need some experience to do that actually. So I don't have that experience. I don't do it myself. So I have my colleagues who are trained in that, so they take care of these small rotors.
So what would be the size of the particle in the solid state NMR?
You mean the amount of samples?
No, size of the particle.
Oh, the particles, it can be anything, the microns or something like that. So that doesn't matter.
Oh, doesn't matter. Okay.
That is just limited by whatever the inherent size of the particle could be. What is important for us is the total amount that you can pack in a given rotor. So if you take the larger rotors, it could be 20 milligrams to 50 milligrams. But if you look at these very high spinning rotors, it could be 1 milligram to 2 milligrams. So the sample volume becomes much smaller, but the resolution goes up tremendously high.
Irrespective of the size of the particle, it can be anything, maybe 100 micrometers. It can be anything, even 1 millimeter also.
Yeah.
Okay.
So we actually even pack the thin films as it is, or we even pack the crystals actually.
Okay.
So we can do that.
The particle size doesn't matter in solid state NMR.
The size doesn't matter. That's one of the main advantages of solid state.
Thank you, sir.
Thanks.
Sir, in solid state NMR also, we need to give the reference like TMS.
Yes. The reference is just like in the case of solution state. The line position is always the chemical shift. The only issue is if I have a quadrupole interaction, then the line position is chemical shift plus quadrupole. So both have to be a reference. So that's why it's a little bit more complicated than the solution NMR. So it's wrong to say chemical shift. If you record an aluminum spectrum, never say it's a chemical shift because it's actually a sum of isotropic chemical shift and isotropic quadrupole shift. So you have to reference it to some aluminum chloride or something like that, and you make it 0. But you need a reference.
Thank you, sir. So there is one question from Dr. Vasanthkumar Bhaskara. So he's asking, can you please comment on magnetic field strength in human subjects of MRI? Will there be any ill effects expected in doing so?
Clinically, I don't accept the current status. If you go by the Americans, I think it is 3 Tesla, which is allowed. But I have seen in Leipzig, they have the 7 Tesla to 9 Tesla magnetic fields, which are used on human beings who are willing to volunteer. Actually, they pay you some money, and then you can go into the 7 Tesla or the 9 Tesla magnet. I did it once. So there's no real issue of the magnetic field as far as I understand. The actual issue is more about the eddy currents, which are caused by the fluctuating radio frequency field. That can be extremely noisy in these kind of atmosphere. The magnetic field is more of a psychological phenomenon as far as I think. It's more of a claustrophobia rather than any effect of the magnetic field. But the on and off radio frequency field can cause eddy currents, and that can cause a bit of motional effects in the brain. But again, it's a transient effect which doesn't have any harmful consequence as far as I understand.
Thank you, sir. Sir, I have another question. This is Dr. Vasan, sir. So I wanted to know, how the applications of NMR in amyloid plaques and in case of drug discovery, if we want to extend this.
Right. So, so the way people look at it is, okay, so the first thing one has to figure out is what is Portioners, or what is causing the neurodegenerative disease. So for a long time, people thought that it is the fibril, but over the last 5-6 years, it's pretty much confirm that it's actually the oligomers, the intermediate species which cause the neurodegenerative disease. I mean, they go into the fibrils at the end of the stage. So what you take out of the brain is fibril, but the neurodegeneration is already caused by the oligomers at a much earlier stage. So one has to understand the transition from the oligomers to the fibril, and from there can we freeze the oligomers and understand the structural properties of the oligomers, and see whether we can come up with the drugs which can actually prevent the aggregation of these oligomers. So that is one of the aspects which people are now looking at. So there is a fair amount of understanding of the structure of the fibrils. That's very clear. But what is important is to get the structural features of the oligomers. And the difficult part there is these are transient structures. They don't live for more than a few minutes. So we have to come up with ways to freeze the oligomer structure in vitro, and then get the special structural properties and understand which element is actually causing these oligomers to eventually aggregate. If you can understand that, and that is worse, there is some understanding of those things, then one has to screen for drugs to prevent the aggregation properties of these molecules. And that is something which people are now trying to do in combination with molecular dynamics. So we have structural information from NMR, and then they screen the drugs computationally, understanding the structure of the oligomers and the fibrils, and see which of these can prevent the aggregation. So that is one way, one line of approach in this case.
Thank you.
Again, I am Vijay Kumar Reddy here. So there are many forms of Corpus equations.
There are many forms of?
Corpus equations. You know.
Yeah.
But I do not know which one to give it to student. If
Yeah,
I refer Pavia, if I refer Pavia, there is one equation. If I refer some, for example, some other book, so I will be seeing some other. Suppose if I see some literature, again there is some equation.
Yeah. So now you're right, of course. So the one which I showed that is the one which has a direct bearing on the scalar coupling, which we measured from the nuclear magnetic resonance, which is like A plus B cos theta plus C cos square theta, etc., etc. So that's the one which, again, as you remember, all of these equations should or would give the same information if you have enough input parameters. The question is, what are the input parameters and how much you are limited by those? But depending upon which, you can refine the equations and get into better structural information. But if you don't have that kind of a luxury, then of course you have to deal with the minimalistic ones, where you might have one parameter to fit in, which looks easy enough, but easy enough doesn't mean that is complete enough.
Okay.
And then only you can think of the next stage. Actually, it's a trade-off anyway.
Okay, because that is a big confusion for us. Which one to give to the student?
I know.
One student,
but that I would think it is really dependent on the parameters that you are able to measure.
If a student refers to Silverstein, he gives one equation. If a student refers to Pavia, he gives one more equation.
Yeah. So in NMR, so we just have this one parameter, the scalar coupling.
Okay. Thank you, sir. Thank you.
So we don't have much luxury in that case.
Thank you, sir.
Sure.
Sir, we have another question here from Dr. Harish Kumar. She's asking, what will be the chemical shift difference between enantiomers? Can you elaborate with an example?
Yeah, I don't have an example over here, but it's again like the hydrogen bonds. It can be 0 ppm to 10 ppm. I mean, it again depends upon depending upon which nuclear spin you look at. It really depends upon the surrounding electron cloud of the different structural forms. Whether it is a bond difference, whether it is some of the hybridization difference or whatever. It is very difficult for me to predict what could be the. I mean, if you show me the surrounding structural configuration, one can come up with a number. Otherwise, the number could be anything actually. And in fact, it is one of these differences which people actually which people use to identify the enantiomers, polymorphs in all these pharmaceutical industries. I mean, you can actually distinguish between each of these species very well. So there I have seen the differences from, it could be even 0 ppm in the worst case, and it could be 5 ppm to 10 ppm in the best case. But it does depend upon the structural configuration around that particular spin.
Thank you, sir. Another question from Dr. Radha Dayanidhi. So she's thanking you for the excellent presentation. So she's asking, among NMR and X-ray crystallography, which is a more precise methodology can be used?
If you need a 3-letter answer, I will say NMR. But I mean, you know, again, if I go back to my, just a second, this is not for the, I mean, I have just taken an example of, biomolecules, but that doesn't matter. You know, I wouldn't say one is more precise than the other. I mean, there are advantages and disadvantages for each one of them. I mean, you can say that X-ray is well-developed, high resolution. It can carry it can cover quite a bit of molecular weight, easy for model building. But of course, hydrogens, motion these are the limitations of the X-rays, crystallization, definitely. But in NMR, the dynamics is something which is, as I kept on emphasizing, that's a niche area for the dynamics. One can get the 3D structure in both solution and solid. You need highly pure sample, not crystalline, but highly pure. One can go up to 40, 50. People have gone up to 100 kilodaltons of late. The resolution content is pretty high. So if you ask, a blunt question as a highly sensitive, it's very difficult for me. I would rather evade that question. So it really depends on the sample that you have, and the information that you are seeking. In fact, people these days, they're going for a hybrid approach of using X-ray NMR and also cryo-EM. The cryo-EM, as you know, for an inhomogeneous sample, even for the oligomers, the fiber kind, the resolution is not that good. The resolution given by solid-state NMR is much greater compared to cryo-EM for such kind of samples. It really is sample dependent to a large extent.
Thank you, sir. Participants, any more questions? I think we can wind up the session. So I request Dr. Shashidhar Bharadwaj to propose the vote of thanks.
Yeah, the session was more interesting and knowledgeable, dear Professor. I appreciate your time and I sincerely grateful for your part in our event and making it more interesting. Thank you, dear Professor, for taking us to fundamental aspects of spectroscopy and teaching very complicated aspects in more simple way. I extend a sincere thanks to our beloved head of the department and to our principal and management for our continuous support. And thank you, dear participants.
Thanks very much.
Thank you, sir, for your time. Thanks, Shashidhar, for the moderations, and thank you all the participants. So we'll start our next sessions at 2 o'clock.
So who's speaking?
Thank you, sir. Thank you, ma'am.
So afternoon, Dr. Pralay Santva from SENS. Yeah, he's talking on XPS.
Right.
Thank you, sir.
Thanks. So I'll take leave then. Yeah. Thanks.
Yes, thank you very much, sir. Participants, please fill the feedback form before you leave the session. Thank you.